The final major topic in our unit on electromagnetism is this idea of electromagnetic induction, arguably one of the most important physics concepts for why our modern world is the way that it is. Now, this is a very big phenomenon, and there's a lot of pieces that goes into it, so we're actually going to break it down into two videos. This one is going to give a brief introduction of the ideas, and then we're going to go into magnetic flux and Lenz's law. So where did this concept even come from, and what is it for that matter? Well, remember, we already talked about that in 1820, Hans Christian Ørsted had published a work saying that electric currents could generate magnetic fields. And many scientists at the time were wondering, well, can we go the other direction? Is it possible to have magnetic fields generate electric currents? And while many physicists and experimenters were trying to figure out if this was in fact the case, there was not really a whole lot of success at first. In fact, it was about 10 years later, in 1831, that Michael Faraday, a British physicist we'll learn much more about later, basically did a series of experiments that began to demonstrate that this could happen in very specific circumstances. So what I want to imagine we have here is we have a coil of wire. Remember, we call that a solenoid, and that is what this is here. It's just wrapped around a hollow cylinder, and we have it connected to an ammeter. Notice that this ammeter can detect currents in both directions, positive and negative. And let's go ahead and set up a magnet right here with its north pole going towards the coil. And what Faraday noticed was that when he brought this magnet into this coil, brought it near it, we would get a small current, but then that would quickly disappear as soon as the magnet stopped moving. Then, when he pulled the magnet out of the loop, the current actually would reverse direction, but then once again go quickly right back to zero. Now, he also noticed that if he went faster with this change, if he went faster into the loop, he would get a bigger positive jump, but it would then again return to zero. And if he moved it quickly out, he would get a bigger negative jump, and then it would return quickly to zero. Well, what happens when we flip the magnet around so that the south pole is going into the loop? When we put the south pole into the loop first, it will actually create a negative in this situation rather than a positive. So the current flips direction, but it once again quickly returns to zero. We pull it back out. It once again goes in the opposite direction, this time positive, returns to zero. And if we go faster, in and out once again, it will spike in the negative direction and then spike in the positive direction when we pull it back out. Lastly, and perhaps more surprisingly, let's say we put a second coil here. And let's connect the second coil to a battery, and we have it connected to an open switch here. So when I close the switch, a current will start flowing in this coil. And what Faraday knows is that when he closed the switch, once again, there would be a small spike in current in this one, even though it has no connection to this battery or this coil over here. And then if he opened the switch again, it once again would have a spike in the opposite direction. So what conclusions was he able to take from all these different experiments that he did? Well, one, that a current would occur in this coil of wire when a magnetic field in the end of the coil, or really, we'll say through the coil, changed. So when he brought the magnet in and out, that changed the amount of magnetic field in the coil, out of the coil, and it changed on the end there. That caused a current to go back and forth. When you have the other coil and he closed the switch, well, remember, when we close that switch, that generates a magnetic field from that current, and that generation of the magnetic field caused a current in this coil. But when the current wasn't changing, that magnetic field stayed the same, no result. When he opened the switch, the magnetic field stopped, so there was a change in magnetic field, so it changed the magnetic field near this coil, and once again the current went. So the magnetic field had to be changing for there to be any noticeable current. The next thing he noticed was that there was a faster change in that magnetic field, and that resulted in a larger current. So when you put the magnet in and out quickly, those current spikes would be larger. Lastly, he noticed when he reversed the direction of the magnetic field, so if he switched the poles of the magnet, or if he, for instance, instead of moving the magnet in, he moved it out, that resulted in a current going in the opposite direction. And when we plug all of these ideas together, we have the basis for what is known as electromagnetic induction. And electromagnetic induction, this is the formal definition here, and trust me, we're going to break it down piece by piece today. The formal definition is that a changing magnetic flux creates a non-localized induced voltage, which will produce an induced current in a conductor. So there's a lot going on there. Let's start off by talking about, okay, well, what do we mean by this magnetic flux? What is a magnetic flux? Because we were just talking about magnetic fields. So flux is going to be a new concept for you, and this is something that comes up a lot in, once again, vector calculus, so higher level mathematics, and additionally in higher level physics. And what flux is a quantity that describes the amount of flow through an area. So I'm going to have some cross-sectional area here, and imagine that this is, I know it looks like just an oval, imagine it's kind of like a circle that's been positioned so that it's coming somewhat in and out of the page, and what flux will do, it will quantify if I have some flow, like with these vectors, through this area, well then that amount of flow we would quantify as the flux. Now there are a few different things that affect the flux through an area. One is simply, well, how much flow is there? If we have less flow going through the area, so less arrows, then you have less flux. If you have more flow going through the area, then that results in more flux. Additionally, what happens if we change the size of the area? Well, if I make the area bigger, more arrows will naturally go through, so we have more flux. And if I make the area smaller, less arrows will go through, so we have less flux. And lastly, what's another way we could change the flux here? Well, let's change the angle between that area and these arrows. And in fact, we get something that looks like this. When we have the area where all of the arrows are hitting it directly, well, that's going to be a point of maximum flux. If we start tilting that area, basically if we start putting it at an angle, fewer of those arrows are going to be able to hit inside, so the flux is reduced until eventually, if basically the area is in the same plane as these arrows, none of the arrows will be able to go through it, and therefore we will have zero flux. So ultimately we are rotating it, and additionally we get a lot of arrows, a lot of flux, fewer arrows, fewer flux, no arrows going through, no flux. Now, we need to be careful here, because if we look at this, your natural inclination is probably going to be, oh, well, the arrows are going this way, the area is perpendicular to those arrows. And then at the bottom, we would say, oh, well, the area is parallel to those arrows. And I totally see why we would think that that's the right way to go about it. Unfortunately, it's a little more complicated than that. When we have a cross-sectional area like this, well, how do we say it has a direction? We usually do it by something known as the normal. Now, if you remember from AP Physics 1, normal force was the perpendicular force, so we categorize areas by what are known as their normal vectors. AKA, if I have the area, the normal vector is the vector that is perpendicular to that area, and we say that is the direction that it is pointed. So looking here at this top picture, it is held up this way, the normal to that area is going to the side, and therefore that normal vector and the vectors going through this area are parallel to each other. So when we are parallel to the normal, or when these vectors are parallel to the normal, that is a point of maximum flux. On the flip side, if we have it like this, well, then the normal to that area would be going down or potentially be going up, but that is perpendicular to all of these vectors. And so when we say that the vectors are perpendicular to the normal, well, then that would be zero flux. So that is a bit of an abstract concept, but what is magnetic flux? Well, magnetic flux is the amount of magnetic field that passes through an area, and usually that cross-sectional area will be the area of a loop or the area of a coil of wire. Therefore, if I look at this really big magnetic field going from the left to the right over here that we label as B, we have a loop of wire of cross-sectional area A in this magnetic field, and the flux would be the amount of magnetic field that is going through this particular area from the left to the right. And the formalized equation for this is, okay, there's going to be a new Greek symbol for you, but the symbol for magnetic flux is either phi or phi. I forget to pronounce both ways. I usually say phi. So this is a Greek letter phi, P-H-I. So phi sub B, so the magnetic flux is equal to B dot A, where B is the magnetic field vectors, and A is this normal vector from this cross-sectional area. Now, a couple things here. What is the unit of magnetic flux is something known as the Weber, W-E-B-E-R, which we abbreviate with a capital W, lowercase b. You don't see it that often, but I want you to know what it is when you do see it. All right, this is a dot product, and we learned about those briefly when we learned about cross products on the right-hand rule. A more simple way to solve for this is simply that the magnetic flux is equal to BA cosine theta, where the magnetic flux is in Webers, B is the magnetic field strength in Teslas, the cross-sectional area A is in meters squared, and this theta here is the angle between the magnetic field and the normal vector to that area. So that would be this angle, for instance, right here. Since all magnetic fields are going this way, that would be this angle there. Now notice that since this is Teslas times meter squared, a Weber is literally defined as a Tesla times meter squared, and sometimes you'll even see it just written that way. Okay, one last thing we want to note here. Remember that if we have it so that the loop has maximum arrows going through it, so it is being held perpendicular to the field, well, that means its normal would be parallel to the field, and this would therefore be 0 degrees. So we would get BA cosine of 0 degrees, or just B times A, the maximum value. If the loop is being held parallel to the field, that means its normal vector will be perpendicular to the field, and it would be BA cosine of 90 degrees, but the cosine of 90 is always 0. So that will result in 0 magnetic flux. So once again, let's return to this definition for electromagnetic induction. It said a changing magnetic flux. So how do we get a magnetic flux to change? Well, there's about 4 different ways we can do it. 1, we can change the strength of the magnetic field. We can turn it up or turn it down. 2, we can change the area of the loop. You can make the area bigger or smaller. 3, and this is arguably one of the more important ones, we can rotate the loop, because if we're rotating the loop, at some moments more of the field will go through it, and at some moments less of the field will go through it. So that flux is changing. And 4, which is also important, we can literally move the loop in and out of the field. So if I move it into the field, there's going to be more magnetic field going through it. If I move out of the field, there will be less magnetic field, so therefore less magnetic flux. So these are the 4 different ways we can change that magnetic flux. But if we have this, it says it creates a non-localized induced voltage which will produce an induced current in a conductor. All right, well, what's that second part mean? So this is essentially what happens. I have this loop of wire here. This loop of wire has some cross-sectional area A, and I'm going to move this magnet closer to the loop of wire, because right now there is no change in magnetic flux through the loop. If the magnet is just at rest, nothing happens. But if I move the magnet closer, more of the magnetic field will go through the loop, the magnetic flux will increase. So if I move this closer to the loop, and when I do that, I will actually get a current generated in this wire until it stops moving. And when I stop moving the magnet, this current will just disappear. And then when I move the magnet away, that's going to create a change in magnetic flux, and we'll actually get a current in the opposite direction, but then once again it will disappear as soon as the magnet stops moving. So this is where the phrase electromagnetic induction comes from. We have a changing magnetic flux. You're changing how much magnetic field is going through the surface area, and when you do that, it literally induces a voltage in the loop or coil or whatever of wire you have nearby, and when that induced voltage happens, that causes a current to flow. So that induction is referring to it being induced, that it is causing it due to this changing magnetic flux. Now the question is, when we get this induced current, how big is it? And in what direction does it go? And there's actually 2 different laws that give us those details. The magnitude is given by something known as Faraday's law. We're not going to focus on that today. That's actually going to be the subject of the next video. So how large or how small this current is. The direction of the current, for instance, if it's going one way or the other, is a result of something known as Lenz's law, which we're going to talk about now. So Lenz's law is how we determine the direction of the induced current as a result of electromagnetic induction. So the idea underlying this law is that the induced current must generate a magnetic field that opposes the change in magnetic flux that induced it. And if it's doing that, that determines the induced current's direction. Okay, it's a lot going on there, so let's kind of go through the details and then we'll look at some examples. So, once again, the induced current must generate a magnetic field that opposes the change in magnetic flux. So let's say there is an increase in magnetic flux going through the loop. Well, if there's an increase in magnetic flux going through this loop, then the induced current must generate its own magnetic field that will oppose that increase. Well, if it's going to the right, for instance, and it's increasing, to oppose that increase, it's going to generate a magnetic field that will be directed to the left, so going in the opposite direction of that initial field. Now, let's say it's going the other way. Let's say the magnetic flux through the loop is decreasing. Well, if it's decreasing, and we're trying to oppose that change in magnetic flux, then the induced current will generate its own magnetic field that, in fact, will bolster the field in whatever direction that is. So if you have a magnetic field directed to the right, but it's decreasing, the magnetic field from the wire will also be to the right because it's trying to oppose that decrease. And lastly, if the magnetic flux through a loop is constant, well, then there's no change in magnetic flux, and therefore there is simply no induced current. We don't need to worry about the direction at all. Now, a way this has often been categorized is with a simple quote that pretty much embodies this, known as "nature abhors a change in flux." So what does abhor mean? That means hates intensely. So nature hates a change in flux. So whenever there is a change in magnetic flux, the results will try to counteract it. So once again, let's kind of reason through this with an example. If I have this loop of wire here, and I bring this magnet towards the loop of wire, well, if we look at it, the magnetic field from this magnet goes out of the North Pole and into the South Pole. So the magnetic field from the north end will be directed to the right, and from the south end will actually also be directed to the right. And if I bring this into this loop, what are we doing? We are increasing the magnetic flux to the right through this loop. Well, Lenz's law tells us that when that occurs, the magnetic field generated by the current in the wire must oppose this change in flux. So if the magnetic flux from this magnet is going to the right and increasing, the magnetic field it generates will need to go to the left to counteract that increase. And if we do that, if we see that these are going to the left through the loop, we can use our right-hand rule and go, okay, well, it's going around this way, therefore my current will have to be going on this side upward and then downward, like so. Now, remember, as soon as we stop moving this, this will stop happening. But then if I pull the magnet back out, I am now decreasing the magnetic flux through this loop. So I'm decreasing the field through the loop to the right, and nature abhors this change. So Lenz's law tells us that the magnetic field now created by this current in the wire will have to also be to the right to bolster it and therefore to counteract that decrease. And if we do that, we can see that if that is the case, I can use my right-hand rule and see that on this side of the wire, it will in fact be going down. But let's say we've now flipped the bar magnet around, and now the magnetic field is directed to the left. And if I bring this in here, we are increasing the magnetic flux through this loop to the left. And if that is the case, well, if we're increasing it, Lenz's law says it should oppose that increase, and it will actually generate a magnetic field going to the right. And if we look, well, what sort of current generates that magnetic field? It would be a current going down the loop here, once again in the opposite direction as we might expect. And if then, okay, remember if we stop moving it, it stops happening. Now if I move the magnetic field out, we're decreasing the flux to the left. We're decreasing the magnetic field in this loop to the left, and therefore it will generate a current that produces magnetic fields going to the left to counteract this decrease, and therefore bolster the field to the left. So the current will be going this direction, and as soon as we stop moving the magnet, this will go away. Now it's probably fair to say that as I went through that, your brain started to hurt a little bit, because it's very, very easy to make a mistake here, because there's so many different right, lefts, increase, decrease, etc. So how do we make sure we don't make a mistake? When we go through Lenz's law, we need to go one step at a time. There's actually 4 steps we need to go through. 1, we need to determine the direction of the initial magnetic field, the magnetic field that this loop is moving through. 2, we need to determine the direction of the change in magnetic flux. In other words, is the magnetic flux increasing or is it decreasing at some moment in time? We need to reverse the direction of the change in flux. So if it's increasing, we need to produce a decrease. If it is decreasing, we need to produce an increase. And we need to go backward with our right-hand rule to determine the direction of that induced current. So we want to create whatever the reverse of that change of flux is. we'll use the right-hand rule to figure that out. So now let's go through an example to try to go through every step at a time. Let's look at this here. We have a loop of wire that is being pulled out of a magnetic field. And since it's being pulled out of the field, there will be a change of flux through that loop because the amount of magnetic field going through it will go down. If it was in the middle of the magnetic field moving around, there would be no change. But because it's at the edge, that matters. So first, let's determine the direction of the initial magnetic field. Well, that's going to be going out of the page. Remember these dots, imagine them like arrows coming towards your face. It's going out of the page. The next is determine the direction of the change in magnetic flux. So as we pull this out of the page, the magnetic flux, or phi sub b, will be decreasing. And a way to really specifically think about this is that it is decreasing and the field is going out of the page. Well, if it's decreasing and the field is going out of the page, to counteract that, to reverse that, we need to increase the field going out of the page through this loop. So now I've gone ahead and drawn the induced magnetic field that we must have to counteract this change in flux. Because of the flux coming out of the page is decreasing, we need to increase the flux going out of the page to try to counteract it. Okay, well, I do that, and now I have to think to myself, okay, use my right-hand rule. If I want this to go out of the page in the center, well, then what direction does the current need to go? And if I do that, I will actually see that the current needs to be going in the counterclockwise direction. Now, if I go in the counterclockwise direction at every point, the magnetic field will go out of the page on every side. If I go over here, it'll be going out of the page in the middle, etc. So we have to do the right-hand rule backward. So why exactly does Lenz's law happen this way? Why is it that the induced current must create a magnetic field that opposes that change in flux? Well, this is really just a result of conservation of energy. Let's imagine it worked the other way. Let's say as I pushed the magnet into the loop, it created magnetic fields that supported it. While as that magnetic flux was increasing, it would generate an even bigger magnetic field in that direction, and that would basically pull the magnet in more, and that would increase the magnetic field, and that would pull the magnet even more, and there would be an even increase, and it basically just goes skyrockets. There's no end to it. So instead, what we need to think about is go detail by detail. When I push the magnet into this loop of wire, it generates magnetic fields in the opposite direction that oppose me doing that. They're pushing against me as I push this magnet in. But that means I'm doing work against this. And when I do work against it, I'm giving it energy, and that energy is being transferred to the charges in the wire, causing the charges to move. That energy comes from me pushing the magnet into the field. When I pull it back out, I'm having to work to pull it because the magnetic fields generated oppose that. So when I pull it, I have to give it energy. Once again, generates currents because I'm giving those charges energy to move through the loop. So there was a lot going on here, but what are our main takeaways for this first video on electromagnetic induction, specifically going over magnetic flux and Lenz's law? Well, one, can we determine the magnetic flux through a loop or a coil using that phi b is equal to BA cosine theta, where B is the magnetic field strength, A is the cross-sectional area in meters squared, and theta is that angle between, remember, the field and the normal, the perpendicular line to that area. We conceptually define the step-by-step process of electromagnetic induction, that by pushing a magnet into and out of a loop or changing the magnetic flux through this loop, that induces a voltage in the loop which will drive the charges and create a current in the loop. And lastly, can we utilize Lenz's law to determine the direction of an induced current, remembering that whatever that current that is induced must generate its own magnetic field that opposes the change in flux. Nature abhors a change in flux.